guys, so we just talked about like what happens when we burn something like coal. When we burn something like coal, we produce a lot of energy, but there's like nowhere near the amount of energy we burn with nuclear energy. Nuclear energy by far produces the most amount of energy. And when we deal with nuclear reactions, we have to deal with what we remember from like isotopes. So like, what is an isotope? So I'll just kind of recap your memory. So you could have carbon-14 and carbon-12, okay? The number on the top just represents the mass. So this is the mass, this is the mass. And then the number on the bottom represents the atomic number. And the atomic number is just the number of protons, okay? So like, for example, the atomic number for carbon, so you gotta take a look at your periodic table. So if I take a look at my periodic table, which is right here, I can take a look and I see carbon right there, and it has an atomic number. This is the atomic number of 6. Okay, so even though the mass is 14 here and 12 here, the atomic number stays the same. The number of protons always stays the same, okay? So it's 6 here, it's 6 here. Atomic number just means the number of protons. And what you're doing is, you can see that this one has more mass, this one has less mass. And the reason for that is because they have different number of neutrons. To calculate the number of neutrons, you gotta go mass minus atomic number. So the mass is 14, the atomic number is 6. That means I have 8 neutrons here. So this one has 8 neutrons. And this one, you would go mass, which is 12. That's mass minus atomic number, which is 6. You would have 6 neutrons here. So you can see that because this one has 6 protons and 8 neutrons, it's heavier because 6 plus 8 is 14. This one has 6 protons, 6 neutrons. This is less heavy, 12. These two are isotopes of each other, right? So there's the same element, but they have different masses. That's what isotopes mean. Same element, different masses, okay? And then there's a table here that you guys can try filling out. The answers are in your booklet. You can fill it in. It's online. Okay, it's on that Google Classroom, so you can fill it in. So that's what an isotope is. Now there's different types of nuclear radiation, okay? So you gotta know all 3 types. So there's like what we call alpha radiation, there's beta radiation, and there's gamma radiation. Okay, now these 3 types of radiation are emitted whenever there's a nuclear reaction, okay? So now when there's a nuclear reaction, there's 2 types of nuclear reactions. There's like a nuclear fission reaction. And nuclear fission means you break apart a nucleus. Okay, remember, we're dealing with just the nucleus. So when we talk about the nucleus, we're just talking about the part that contains protons and neutrons, okay? We're not talking about electrons. That's chemical reactions that involve electrons. We're dealing with nuclear reactions. So basically when you break apart a nucleus, boom, that's nuclear fission. Nuclear fusion is what we learned about what happens in stars. So nuclear fusion is when you have one nucleus, okay, so like a hydrogen plus another hydrogen nucleus, and they fuse together to create something bigger like helium. That's a nuclear fusion reaction. Fusion reactions produce the most energy. These reactions from stars produce the most energy. And whenever you have this fission or fusion reaction occurring, you produce 3 types of radiation. This alpha, beta, and gamma radiation. Now, alpha radiation is made up of 2 protons and 2 neutrons, and it has a charge. It's right here. I'm going to show you guys. You guys got to go to this page here. This is page 8, and it tells you what an alpha particle looks like. And it tells you what a beta particle looks like. And it tells you what gamma radiation looks like. So what is an alpha particle? An alpha radiation produces alpha particles. Okay, so alpha radiation produces alpha particles, beta radiation produces beta particles, and gamma radiation produces gamma rays. Okay, so what is an alpha particle? An alpha particle, right, it shows you on this page, page 8, helium-4, 2. Helium-4, 2, that's an alpha particle. Okay, and then what's a beta particle? It tells you right here. It says it's an electron with 0, -1. And what's gamma radiation? It sort of looks like this Y symbol right here. So gamma radiation, or a gamma particle, looks like this, and it's 0, 0. Okay, so the alpha particle is the heaviest. So whenever you have a nuclear reaction and you release these alpha particles, they're heavy, and your skin can stop it because they're big and heavy. If the nuclear radiation releases beta particles, these are smaller, aluminum can stop it. If you release gamma radiation, you guys need a lead suit to stop gamma radiation. So gamma radiation can pass through your skin, can pass through aluminum, and it is only stopped by lead. So gamma radiation is the hardest and the most, the worst for you because it's so penetrative. It penetrates so well. Alpha radiation has very low, it doesn't penetrate very well, so it's low penetration. Beta radiation is kind of medium. It can go through skin, but then it's stopped. Gamma radiation can go all the way through skin and bone, and the only way you can stop gamma radiation is with lead suit. So like if you're ever in a nuclear accident, the best way to stop all three is to wear a lead suit that stops the alpha, beta, and the gamma radiation that's released, okay? Okay, so you guys can see that when you do, these are nuclear decay reactions. So we're gonna do some together. So that's on page 16 of your book. So what we're gonna do is you guys gotta know how to work with nuclear reactions, okay? Like how to do this. So like for example, it gives you this. It gives you plutonium 242, 94, and it's telling you this undergoes a nuclear reaction. So this is the reactant, and it's undergoing a reaction, and it's producing helium-4 and 2. So it's actually going under what we call an alpha decay. It's called an alpha decay because this is decaying or breaking down into an alpha particle, which is that helium. And then it's asking you, what else does it produce? Okay, well, if this is breaking down to make helium, that means this plus this element that it produces, this other element it produces, has to equal this 94, which is the atomic number. So basically, like, remember the atomic number is the bottom number here. I just said that. This is the atomic number here. So is it true that 2 plus 92 makes 94? Well, if you want to know what has an atomic number of 92, you guys can look at your periodic table. And you guys can find number 92. And you can be like, okay, 92 is right here, uranium. So guess what? You made uranium. So look at your periodic table. It'll tell you, remember, this top number is the atomic number. So 92 here. 92 plus 2 would make that 94. And then what number would go up here? It would be 238. 238 plus 4 makes 242. And that's what you made when you had alpha decay. So you can see it's like not that hard. We can do another one. So what is it says, do the alpha decay of radium 226. Okay, so if you want to do the alpha decay of radium 226, radium 226, this 226 refers to mass, okay? This number at the back, if you write it out like that, that 226 refers to mass. So you take a look at radium. Okay, where are you, radium? It's right here. It's number 88, radium. Okay, so radium, right, has 226 is the mass, goes up here, and 88 is the atomic number. If you're doing an alpha decay, that just means you're making this alpha particle, helium-4, 2. Okay, so if you're making that, then what's the other element you're making? Remember, this plus this number here has to equal 88. So this number has to be 86. So what you guys do is you look at your periodic table and you say, okay, what element is element 86? Oh, here it is. It is right here, guys. Radon. Radon is 86 right here. So radon is 86, and that's 2. And so what would be the mass? It would have to be 222. 222 plus 4 gives you 226. And that's how you do that alpha decay. Now, you will be asked to do beta decay as well. So when you do beta decay, we'll do a beta decay with you guys. Beta decay just means you're producing a beta particle. So beta decay is, let's say you want to do beta decay of polonium-210. Okay, so polonium-210 means polonium has a mass of 210. That's the mass. Okay, so you can find polonium on your periodic table. Polonium, polonium, where are you? Platinum. I don't even know. I never can find these things. Right here. Here's polonium. Polonium is 84. That's the atomic number. So we write out polonium 84 at the bottom and 210. Okay, remember the atomic number always is at the bottom, the mass is at the top. They give you the mass. You find the atomic number on your periodic table, which is 84. And it's undergoing beta decay, which means that it's producing an electron 0, -1. That's what it's making. So that means what other element is it making here? Okay, well, this number is 84. So if this is a -1, that means this has to be 85. Because 85 minus 1 makes 84. And 85 is astatine. Astatine? So that means we're making astatine here, okay? Okay, remember this has to be 85 because we need these two numbers to equal the number. The numbers on the product to equal. So 85 minus 1 is equal to 84. And that means this is 210 here. Because if this is a 0 here, that just stays as 210. Right? That's how it works. Because these numbers on this side have to equal the numbers on that side. And that's how you do a beta decay. You guys can try these practice problems here on alpha and beta decay. It will help you kind of understand it. You can ask me if you have any question. I mean, we can even do this one together. If you have 1508 oxygen and you make 0E -1, then what else are you making here? Well, remember this -1, this has to be a 9 here because -1 plus 9 will give you this 8. And then you take a look at your periodic table and you see, okay, what has an atomic number of 9? Hey, that's fluorine. And what number would go on the top? Well, there's a 0 here, a 15 here, so 15 plus 0 is 15. And there you go, you have fluorine. Okay, so that is that. You can try these practice problems to help you guys out. Now, the last thing that you guys are gonna do, so this talks about nuclear fission and fusion, which I kind of already did with you guys and what the difference is. This is talking about a can-do reaction. So that a can-do reactor is just a nuclear reactor. And basically what you're doing in a nuclear reactor is you're doing a fission reaction. So like in Ontario, they have nuclear reactors. And basically they take a neutron and they fire it into a nucleus, and they break the nucleus apart. That releases like enormous amounts of energy. And that energy is used to heat steam, heat water, to make steam. And that steam, right? So you have this nuclear fission reaction. And that's because the nucleus has intranuclear potential energy. Meaning energy is stored within the nucleus. That's intranuclear potential energy. Energy stored in the nucleus. You're going to heat water, which is like thermal energy, to produce this fast-moving steam, which is kinetic, which turns the turbine, which is also kinetic, and that creates electricity. Okay, again, we're dealing with a generator where you move or spin that wheel, turbine, and you generate electricity. Okay, so that's it for that. It goes through advantages and disadvantages of using nuclear reactions. It does that with coal too. The disadvantage of nuclear reaction is it's a pretty clean energy, but it's non-renewable. So once it's gone, just like coal. Also, if it leaks, we're in trouble, right? Because if it leaks, you could release tons of gamma radiation, and that's not like good for you. It could cause like cancer. Okay, today's last thing is going to be on E equals mc squared, which is my last equation, which is Einstein's equation. E is equal to mc squared. And this is the change in mass times c squared. So this c squared is actually the speed of light, and that is given to you. Okay, speed of light is given to you. 3.00 times 10 to the 8th. Just forget what page it's on. Right here. It's on page 3. 3.00 times 10 to the 8th. So C is equal to 3.00 times 10 to the 8th meters per second. That's the speed of light. This just tells you it's change in mass. So basically, it's saying that Einstein came up with this equation that you release energy if you have a change in mass times the speed of light. So a change in mass will create an energy release. And what you guys got to do in order to do this equation, it's so easy, again, is you got to use this page in your periodic table, page 8. You're going to be using that table, okay? So we're going to do an equation together. So let's just do one together and you'll see how easy it is. Using E equals mc squared, you're going to calculate the energy released by the alpha decay of radium-226. Okay, alpha decay of radium, so you're going to calculate the energy released by that. So radium is right here. Radium-226 is that. It tells you this on page 8. So you have radium-226. So we're going to write that down. Radium-226, 88, produces an alpha decay. An alpha particle is right here at the top. Helium-42. Helium-42. And remember, if it's an alpha decay and it's 4 and 2, then what's the other one you're going to make here? Well, 2 plus 86 will make 88. So 86 is, the atomic number 86 is radon. So you're going to make radon, and it's going to be 222. And that's your alpha decay that you just learned and you understand. Now, when you want to calculate the energy released, you're going to again do the sum of the product minus sum of the reactant, the same formula that we did in the last lesson we're doing here. So again, on this side of the arrow here, these are your products. And over here, this is your reactant. Okay, so now what numbers do we associate with the products and the reactant? We got to use this table here. Okay, these are the masses given to you. See right here. So you can see, and you got to use the whole mass, okay? What the masses are here. 88, 2, and 86. So the mass of radium-22688 is going to be 226.02540. And then you guys, it's all 10 to the negative 3. So this is times 10 to the negative 3. And then the mass of helium is given to you right here. Again, it's times 10 to the negative 3. So the mass of helium is 4.00151 times 10 to the negative 3. And the mass of the radon is 222.01757 times 10 to the negative 3. Okay, and again, you guys are doing the mass of these two. You got to add them up. Sum of the products minus the reactant. So you go 4.00151 times 10 to the negative 3 plus 222.0175 times 10 to the negative 3. And you guys, you can put that in your calculator. It's kind of this weird thing that you're doing, right? 4.00151, oops. 4.00151 times 10 to the negative 3 plus bracket 222 point, oops, delete, 222.0175 times 10 to the exponent negative 3 bracket equals, okay, so there you go. That's the answer, 226.01901. That is the product, okay, and the reactant is that number. So you got to minus the product from the reactant, okay. So you got to minus the product, which was that number that we found, 0.226.01901 minus reactant, which is 226.02540 times 10 to the negative 3. Okay, so this is the sum of the product minus the sum of the reactant. We only had one reactant, so we only use the number here for that. Okay, sum of the product minus sum of the reactant, and so then I go minus 226.02540 times 10 to the negative 3 bracket is equal to, so my answer then becomes 6.39 times 10 to the negative 6. Okay, so that's my change in mass. Okay, so I calculated the change in mass by using the numbers on my periodic table. Not a periodic table, sorry, numbers on page 8. And then I do E is equal to mc squared. The change in mass is that number. C squared is 3.00 times 10 to the 8th. So that means E is equal to 6.39 times 10 to the negative 6 times C squared. You got to square this number, 3.00 times 10 to the 8th. You got to square it. And then when you do that, your answer should be 6.0 times 10 to the negative 11. 5.7. So if I was at times to the 11th joules. And that's how you do it. Okay? So that's all you do. So remember, to calculate the change in mass for E equals mc squared, you're going to need this table. Okay? Product minus reactant. Then times it by C squared. Try these questions in your book. See how you do. Okay? If you have any questions, you can ask me. We're done. The lesson is done. There are some questions that you guys can do here. Right here, try them. See if you can get the right answer. And here's some multiple choice questions you guys can try if you'd like. And then we're done. Okay, and we'll start the next part next week. Okay, bye guys.